Okay, here we go. Homework for tonight. All right, so this lesson continues with the chapter on similar figures, and we will specifically do similar polygons. Three objectives. All right, it's an easier day than the last one if you can remember what we did the last time. So think about this. I have clearly have a triangle there. That's triangle ACB. And if you're familiar with PowerPoint or anything that deals with pictures, you know that if you click on a picture, you remember you kind of get this thing. And then if you want to increase the size of it, you take either the upper corners, one of the left, right, top or bottom, and you simply drag it and you make a bigger one. And one thing we notice is that if we do an upper corner versus a top, bottom, left, or right, the little squares there, is that it maintains a proportion. In fact, it maintains the shape. It doesn't distort the shape. It just makes it larger. And that's what today's concept is about. The concept of sometimes you can have the same shape, but different size, but the proportions all remain the same. In other words, all I'm doing is increasing the size. I'm not stretching left and right or up and down. I'm stretching both at the same time. Therefore, I maintain the proportions. All right, so are these triangles the same? Clearly not. One is small, one is large. All right, so we have a concept in math about this. And if we take the same triangle and increase its proportion, then we can't call it triangle ACB anymore. So the first thing is we give it a new name. And that new name, it is customary to use these little tick marks. You see that on all the letters on the vertices, and that is called prime notation. So we would say triangle ACB and triangle A prime, B prime, C prime. All right. And once again, the concept we have is when you change the size, but not the proportion, is that it is a similar shape, not the same shape. Certainly not equal or congruent. It is now similar. All right. So there's a couple things about similar. First and foremost is that it maintains the same angles. Now I made an equilateral and equal angular triangle there, ABC, and if I just increase its size, it is still an equilateral or equal angular triangle. So for instance, the angles of an equal angular triangle are 60 degrees for each one of those angles A, B, and C. Therefore, for triangle A prime, B prime, C prime, the angles are also still 60. Clearly, the sides, though, have changed. So the second thing is, or here, give you an example. So for instance, if I scale this by a factor of 3, in other words, I increase the size by a multiple of 3, then A prime, C prime, or that side there on the left, is now 6 units. All right. So the second thing is that the sides have been scaled up by a specific factor, not a different factor. All the sides have been scaled up. So on this one right here, I scaled it up by a factor of 3. All right. We'll write this down here in just a second. So similar is a fairly straightforward, easy idea. There's only two consequences. We'll write it down here in a second, but it has a complicated definition. So take some time to understand what I'm saying here, write it down, replay the video if necessary. So here's the definition. You need to write down everything here. If it helps to draw the two triangles, do that as well too. So first off, the formal definition of similar, and specifically for polygons, are two polygons are similar if their vertices, that would be A, B, and C, can be paired with another triangle's vertices, A prime, B prime, C prime, so that two things occur. So two key consequences. Consequences number one is that the angles are congruent, corresponding angles. So A with A prime, B with B prime, C with C prime, they still are congruent. Just like for congruent triangles, for similar triangles, the same thing happens. All the corresponding angles will be congruent. It's consequence number two that's a little bit more challenging. Consequence number two is that the sides form a proportion. Well, if you remember, that was literally the last thing we did in this chapter, which was proportions. All right, so let's explore that. Oh, and lastly, we have a symbol for similar. We can't use congruency symbol, so we don't use equal, we don't use congruency, we just use the tilde right there, this red thing right here. So if I want to say those two triangles are similar, not congruent, then I would say that statement right there. So triangle ABC is similar to triangle A prime, B prime, C prime. Okay. You don't always have to use tick marks. For instance, if the second triangle had completely different letters, D, E, F, we could say triangle ABC is similar to triangle DEF. We'll see that as well too. But if we scale up a specific triangle, it makes sense to maintain the fact that it came from triangle ABC, hence the A prime, B prime, C prime. Okay. All right, so we're going to explore the two consequences for a second. Just like we had a congruency statement for congruent triangles, we have a similarity statement for similar triangles. So if you remember right, with the congruency statements, we could tell something. We could tell the corresponding sides and the corresponding angles. Remember doing this? The first letter goes with the first letter. A, B goes with A prime, B prime. Same thing. All right. So remember the two consequences are the angles are all congruent or corresponding angles are congruent. So for instance, A goes with A prime, B goes with B prime, and C goes with C prime. It's the second one that the corresponding sides of proportion we need to look at in detail. So let's look at what that means that the corresponding sides form a proportion or are proportional. All right, those are the two key consequences. All right, so what I'm going to do is I'm going to just throw some numbers up. So I said I made an equilateral triangle. So the first triangle ABC is going to have side lengths of 2, 2, 2. And if I scale that triangle up by a factor of 3, I could have picked any number, but I picked 3, then the resulting triangle had side lengths 6, 6, and 6. Okay. Um, hmm. Now what am I going to do? Well, it says make a proportion. So you have a choice. You can either start with the small triangle or the large triangle. It doesn't make a difference. I'll start with the small triangle. I'll pick one side. So I'll pick one side, AC, and its corresponding side, A prime, C prime. See what I did? I didn't have to pick the small one. I could have started with the large one, and then I could have picked any one of the three sides. I write its corresponding side as the bottom part of that fraction, the denominator of the fraction. Okay, cool. So what would that equal? Well, AC is 2 and A prime C prime is 6. That reduces to 1/3. Just for a second, I'm not going to reduce. Well, let's pick another sides. Now, I've already established the pattern of small triangle compared to large triangle, so I'm going to stick with the small triangle and pick one of the other two sides. So I will pick CB. And by the similarity statement, the corresponding side with CB is C prime B prime. Now let's look at the C prime B prime underneath CB, and well, that is also 2 over 6. Lastly, the third side, you can probably guess, the third side is also equal to 2, 6. So all of the sides, as long as I go small triangle over large triangle, the proportion is equal to 2, 6. That is going to be very convenient and helpful for us to do the homework tonight. So this is what it means by the sides are in proportion. Now, the statement won't have 2 over 6 because they're talking about just a general set of triangles. So the statement will look like this. Or, now remember, I could have started with the larger triangle. If I start with the larger triangle, so the numerator side is the larger triangle and the denominator side is the smaller triangle, then it would look like this. Either way is fine. But there are two main consequences. The angles are congruent if they're corresponding, and the sides form a proportion. The only thing that's weird here is that for the sides, you have to choose how to write the proportion, and there's two ways to write it. Small over big or big over small, your choice. All right, if that doesn't completely make sense, rewind the video, play it again. All right, so what do we do with this? I said today was an easy day. It is, right? We're going to do the same thing we did with congruent polygons. And if you remember, after I introduced congruent polygons, we did two basic things. The first skill was we identified the corresponding angles. And then the second thing we did was we identified the corresponding sides. So for similar triangles, we're going to identify the corresponding angles, and we're going to identify, this is the only change, the proportional sides. All right. You can get this either, same thing with congruency statements. You can get this either from the diagram or from the similarity statement. Either one works. And you know me, I always recommend getting it from the similarity statement to make your life easy. All right. So let's see a concrete example. So we don't have triangles here. We have pentagons. And it states, let's see, what it states right here that they are, in fact, similar. You see the similarity indicator right here, the symbol. So we're told that they are, in fact, similar. Okay. And then we're told to list the congruent angles. So once again, I would recommend using the similarity statement. So I would recommend using this and this rather than looking at the picture, although this particular picture is fine. So let's see. It makes sense to start with left to right, so we'll start with angle P. So angle P corresponds to angle V, okay? Angle P corresponds to angle V. And then moving right along, T goes with Z, S goes with Y. You see what I'm doing? R goes with X, and lastly, Q goes with W. So that's pretty straightforward and easy. What's the next thing we have to do? We have to list the proportional sides. So now we have to make a choice. You can choose either small over large or large over small. And what I mean is not small and large sides, I mean small and large polygon. I have a small pentagon, I have a large polygon. So when I write the proportion, the two ratios that are equal to each other, I choose how to write them. I'm a creature of habit. I always go left over right, so I'm going to do the small polygon over the big polygon. Now I need to pick a side, so I'll just go with the first two letters, PT. So let's see, that would be PT over VZ. So PT over VZ, right? I just choose that. And then I continue down the process. What's the next side? Well, let's see, after PT, I got TS. So TS would be equal to ZY. Do you see what I'm doing here? Then SR would be equal to YX. And lastly, I'm sorry, there's five sides. Then RQ is to XW. And pretty straightforward and easy. Pretty straightforward and easy. For some reason, I left off PQ and WV. Hmm. Make sure that you list all of those. So that is a mistake right there on the slide. I should have listed PQ and VW, but I didn't. All right. How about we go to a triangle? Let's try not to make a mistake right here. All right. So for the triangle, let's see. There's no shape here, or there's no diagram here. I just have the similarity statement. So this is actually a little bit easier. So the congruent angles, A goes with G, D goes with H, and X goes with Z. And for the proportional sides, once again, I don't even know which triangle is large and small. I'm just going to go left to right. So let's see. Side AD over GH is equal to D8 or DX over HZ is equal to XA over ZG. All right, I did that one correct. Pretty simple. Hope so. All right, moving on. Here's a definition. All right, let's say I have two similar triangles or two similar polygons in general, and I can tell something about their side measurements. So the one on the left has a side, AC has a side measurement of 2, and the one on the right, its corresponding side, A prime, C prime, has a side of 6. We saw this. That was the example I started with. So scale factor is how did you make the small one into the big one? Or how do you make the big one into the small one? That is called the scale factor. And to create a scale factor, you just take one set of corresponding sides and their values, and you write a ratio. So the ratio of the lengths of two corresponding sides, 2 over 6, right? Here's the formula for it. Look, there's more to this formula than is necessary. It's just simply the way it has to be written. So it says the length of shape 1 over the length of shape 2, but it's got to be the corresponding sides. So it has to be these corresponding. I can't just pick any two sides with numbers. It has to be the corresponding sides. Okay, so it takes longer to write that formula than to actually do it. So if I went big to small, that would be 6 over 2. If I went small to big, it would be 2 over 6. You see what I'm doing here? And you're like, well, why didn't you use the one with the numbers? Well, remember, it can be any one of the corresponding sides as long as you have values. Okay. So how do I use all this? So here's the example with the scale factor. All right. So it says calculate the scale factor. Well, notice here on these two pentagons, there's only two values. So I don't have much to choose from. So the scale factor is either small to big or big to small, your choice of how you write it. So let's see. If I do small to big, right, that would be PQ over VW. That would be 20 over 32, which reduces to 5 over 8. And as a decimal, you'll see why I'm doing that here in a second, it's 0.625. So think about this, grab your calculators. If you multiply the big number 32 by the scale factor 0.625, you get the smaller number 20. Check that out with your calculator. If I want to go from the small to the big, then I simply write it in the opposite way. Instead of putting the small side over the large side, now I'm going to put the big side. So this is called scaling down when you initially put the small over the big. If I put big over small, I'm going to get a number that's bigger than 1. That would scale it up. And I want you to notice right there when I wrote that answer, notice the relationship between it and its cousin directly above it, and notice that they are in fact reciprocals of one another. Ooh, that's going to be convenient. If I convert 8 over 5 to a decimal, it's 1.6, and take your calculators again, multiply 20 by 1.6, and notice you do in fact get 32. Boy, is that going to be convenient for us to solve for unknown variables. All right, so it's important that you understand scale up and scale down. So once again, if you want to scale something down, make it smaller, you need to start with a ratio of the small over the large. That would give you a number that's between 0 and 1. If you want to scale something up, you start with the large side, 32. So 32 over 20 will give you a number larger than 1, and that's how you scale something up. Okay. So this is going to be this is like homework. This is going to be a very messy slide. Don't be lazy. Pay attention. Pause the video. Try to get to the answer before I get to it. So there are 4 questions right here. It says scale factor. It says calculate X, Y, and Z. It says calculate the perimeter and then give me the ratio of perimeters. Okay. So the scale factor, we just need to pick 2 sides that have values. I can't pick sides that have an X, Y, and a Z. I need to pick 2 sides, corresponding sides, that have numbers. And if you notice, if you look all around, let's see, there's only 2 sides that actually have numbers that are corresponding, DC and D prime C prime. So let's see, if I did small to large, that would be 20 over 30, which will reduce to 2/3. And so that would be scaling down. And if I did large to small, that would be 3 over 2, just the reciprocal. The scale factor itself, you don't need to calculate both. You really only need one. And it's just your choice which one to use. All right, so that's the scale factor, small to large, or how to scale something down. Let's see if we can now calculate X, Y, and Z. Doesn't really matter which one we start with. We'll start with X. If you notice that X, its corresponding side, A prime, B prime, is 21. So if I wrote the value of X side as a ratio, that would be X over 21, or AB over A prime, B prime. Do you see what I'm doing? Well, since it's a similar polygon, then it must have the same scale factor. So that must be equal to X over 21. That must be equal to 2/3 because that's the scale factor. And this is why we spent all those time last class solving proportions, because now you need to solve that proportion. So let's see, cross multiplication, 2 times 21 is 42, and 42 divided by 3 is 14. I'm going to skip some of the math here. I'm assuming that you know how to solve your proportions. All right, so X is done. How about we do Y? Do the same thing. Let's see, I got Y. Y is on the big one, and 8 is on the small one for corresponding angles. Now remember, our scale factor is from large to small, so we need to be careful that I'm sorry, from small to large. Now I said it correctly, 2 over 3, small number to big number. So I need to make sure I set my proportion correctly. If I were to write y over 8, then I would have to use 3 over 2. If I use 8 over y, then I can use my 2/3. Do you understand what I'm saying here? So 8 is on the small, y is on the large. So I would need the scale factor of small to large, and that's 2 over 3. If I were to choose the other way around, y over 8, then I would need to use 3 over 2. Make sure you understand that. Rewind, play that one again. All right, cross multiply. 8 times 3 is 24. Divided by 2 is 12. Which leaves z. Let's see, where is z? Z goes with 10. So same process again, small over large. So 10 over z is equal to 2/3. 10 times 3 is 30, divided by 2 is 15. So I've got x, y, and z. We're not done yet. That's only halfway through. All right, perimeters. So what are the perimeters? Well, I now know all of the sides. X is 14. So on my small quadrilateral right there, I would have a perimeter of 10 plus 20 plus 8 plus 14. And on my big one, let's see, the y is 12 and the z is 15. So I would have 30, 12, 21, and 15. So for my small one, I get a value of 52. For my big one, all I'm doing is substituting 12 and 15 for a z and y. I get a perimeter of 78. Cool, easy to do, but here comes the watch this. It says give me the ratio of perimeters. I got a perimeter of 52, I've got a perimeter of 78. You want to take a guess what it actually equals? If I do 52 over 78 and I reduce that fraction, let's see what goes into 52 and 28, and that would be 26. 26. Well, that's going to give me a 2 to 3 ratio. If you don't believe me, go ahead and reduce that ratio by twos a couple times, and you'll see it goes into 2/3. Or you can divide 68 by 26. 78. Why did I say 68? Okay, so that last one was a whole lot of work, but that's where the class ends up. Once again, they're going to give you similar or non-similar shapes and ask you some questions, why or why not. And then this is similar to the one that we just did right there. All right, so there's your homework. As always, if you have any questions, send me an email, see me in the hallway, and I will see you in the next class.